I'm Chester Harvey, a PhD candidate at UC Berkeley, where my research focuses on travel behavior, urban design, and computational methods. This paper comes out of a thread of my research where I investigate how streetscape design may be used to promote sustainable transportation. Analyses of relationships between transportation and the built environment have tended to focus on neighborhood-scale built environment characteristics, such as land use entropy and street connectivity. Streetscape scale influences continue to be poorly studied in a transportation context, and this is despite a lot of research in the field of urban design that points to the importance of streetscapes for shaping the preferences and behaviors of users, such as pedestrians. A major reason for this dearth of research may be that streetscapes are simply difficult to measure across samples that are large enough or spatially distributed enough for transportation analyses. This paper explores a radically simple approach to representing streetscape design in a way that facilitates such widespread analysis. I call this simplified measure building distance, and it's just the straight line distance between street centerlines and the nearest building measured at regular intervals. Building distance is lower when buildings are either closer to the street, or the street itself is narrower, or when buildings are spaced more closely together. So how might this measure be useful? Well, walkable urban design qualities are often promoted by close proximity between pedestrians and buildings. Enclosure, for example, is accentuated when buildings of a given height are closer to an observer. A streetscape is more human scale in its horizontal dimensions when buildings are closer to the street. And qualities that depend on users perceiving and exploring the built environment, such as transparency, complexity, and imageability, are likely strengthened when buildings are closer to them, and therefore more accessible and perceivable. Reducing distance between streets and buildings is not universally necessary to produce these qualities, nor does it necessarily guarantee them. However, building distance may provide a useful and also extremely straightforward indicator of where these qualities are more or less likely to exist. To demonstrate and explore the building distance measurement, I developed Python scripts to calculate it across entire urban regions. I then calculated building distance across each of the 100 largest urban areas in the US. These histograms show the distributions of building distance, averaged within block groups, across those 100 urban areas. Building distance is fundamentally a measure of construction density, so it's unsurprising that a dense region like New York would have some of the lowest building distances, and also a fairly tight distribution, owing to the consistency of streetscape forms within that city, with buildings closely spaced and also close to the street across most of that urban area. Raleigh, by contrast, is more suburban in character, with larger rights-of-way, setbacks, and distances between buildings that yield larger building distances. Design theory would suggest that New York, with its smaller building distances, is more likely to be walkable than Raleigh, but clearly these relationships are also more nuanced than these regional averages might suggest. Los Angeles, for example, has fairly low building distances, but also notoriously low rates of walking, while Honolulu has fairly high rates of walking and greater building distances on average. So it's clearly important to examine how building distance may interact with other localized factors, or may even have nonlinear effects on walking behavior. To assess the potential for using building distance as a covariate in transportation modeling, I examined relationships between building distance and built environment measures that are conventionally used in such models. This graph shows the distributions of Pearson correlations between building distance and each of the labeled variables across those 100 urban areas. You can see that building distance tends to be most strongly correlated with intersection density and population density, which makes sense given that it's also a density measure. Correlations with these other built environment variables are in the expected directions, but they're only low to moderate in magnitude, which suggests that building distance provides a substantially different measure. Therefore, it's possible that building distance could represent how users perceive streetscapes in ways that aren't already accounted for in transportation models. My ongoing work investigates the efficacy of representing streetscapes with the building distance measure compared with more complex measures of qualities such as enclosure and transparency. I'm also examining how these qualities affect both the stated preferences and the revealed route choices of pedestrians. The greatest utility, though, of such a simplified building distance measure may be in examining geographic differences in preferences by drawing comparisons between cities, something that can really only be done with a highly reproducible and efficient measure like building distance.